This video is intended to give you all the important need-to-know information that you need to decide what's the right starter scope for you. Now, telescopes do two things. They allow you to see faint objects and they allow you to see small objects. Faint objects tend to be outside our solar system and they tend to be big and fuzzy. The so-called deep sky objects, galaxies, globular clusters, nebula, supernova remnants, and so on. The small objects tend to be bright, double stars, star clusters, planets, and so on. Magnification is largely a red herring here. It's basically all about aperture. The ability of a telescope to see faint objects basically goes with the square of the aperture. So that is, if you double the size of the aperture, you get 4 times as many photons, and that allows you to see much fainter objects. The larger the diameter of the telescope, the smaller the object the telescope has the capability to see. But this time it basically goes linearly with the aperture. That is, you double the aperture, then you can see objects about half the size. So where's the problem, I hear you ask? The bigger the scope, the better, right? Well, to a degree, yes. However, there are other limitations on the telescope. The first and most obvious is the sky. All scopes are essentially useless under a cloudy sky, but even if it's not cloudy, the sky is commonly a greater limiting factor than the telescope. If you're looking at faint objects such as nebula, these tend to be big and fuzzy, and so the darkness and the clarity, that's basically how transparent the sky is, are the principal factors. If your sky is murky or has a lot of light pollution or there's even a full moon in the sky, you can largely forget about it. A big scope under those circumstances is just an expensive way of making it hard to look at the stars. Small objects tend to be bright, like planets and double stars, so the clarity of the sky is not terribly important. However, the stability of the atmosphere is crucial. That shimmer you get on a hot road? Well, the moon is about half a degree in size, and a big planet like Jupiter is about 1/60th of the angular size of the moon. And a good scope can, in principle, resolve up to about 60 features across that disk. So as you can imagine, you need a very still atmosphere to fully capitalize on that. The bigger the scope, the stiller you need the atmosphere to be to take full advantage of it. Indeed, for resolution purposes, once the scope gets up to about 30 centimeters or 12 inches in diameter, the atmosphere is essentially never stable enough and always limits the performance of the telescope. So let's assume for the moment that the skies are excellent. The next major factor is ease of use. Most scopes are not permanently set up, and so they have to be moved outside and set up. A scope that weighs as much as a small car might have superb capabilities, but if it takes an hour to move outside and set up, experience has shown that it'll simply tend not to be used. Typically, the largest scope that can be handled by one person is about a 6-inch refractor or a 12-inch reflector type scope. And because telescopes typically deal with resolving such small objects, the telescope's performance is frequently atrociously subpar until it is cooled down to about the outside temperature. And the larger the scope, the longer that takes. It really all depends what sort of astronomy you're going to be into. If you just want a scope that you can take out into the garden and stargaze for half an hour or so, having to set things up and let them cool down for half an hour or so can have a significant deterrent effect. Now, the scopes themselves come in 2 basic forms: those that focus the light by lenses and those that use mirrors. Those that use mirrors typically have a secondary mirror in the optical train, and this obviously reduces the light gathering capability of the telescope and also lowers the resolution. In practical terms, what that means is you get more contrast images out of refractors. But most refractors have the problem that they focus the red light and the blue light in different areas, the so-called achromats. Pragmatically, that means that bright objects like planets get this purple halo that you cannot get rid of. Well, cannot. You can do it by putting extra lenses in the optical train, the so-called apochromatic refractors, but that makes the scopes cost about 10 times as much as an equivalent aperture reflector type scope. Having said that, I have used these scopes under dark skies and they are almost magically beautiful to use in the way that the stars fall, if you'll excuse the poetic language, into impossibly sharp pinpricks of light on a black velvet sky. Now you need to mount the scope. You see, when you're looking at this very small portion of the sky, first of all, of course, you need a very sturdy mount. That's really important. But secondly, the Earth's rotation becomes a bit of a bitch. The Earth is hammering around such that the sky apparently rotates, well, once per day. And if your scope's not driven to compensate with that rotation, you'll just observe the object you're looking at drift out of the frame depending on the power, but typically in about a minute. The undriven mounts, of course, are much cheaper, but you have to compensate for the Earth's rotation by actually moving the telescope, and that can be a pain. Driven scopes these days are almost exclusively the so-called go-to scopes. Go-to scopes basically require your location on the Earth, the time, and a few star observations such that the scope knows in which direction it's pointing, such that you can drive the mount to track objects. The setup might only take 10 minutes or so, but it's still a pain in the ass, and even more so if you don't have a good idea of what you're doing. However, after that, most scopes will allow you to request an object, which the scope will then dutifully find for you. But if the scope gets nudged or moved, you'll typically have to realign it. Now, the go-to mount can save a lot of time in messing around with star atlases and finders, but it also removes a lot of the organic feel of exploring and getting to know the sky. The scope just pans and tilts, and after that all you do is look into the eyepiece. So these are the basic metrics you need to assess when choosing which scope is right for you. After that, it basically boils down to how much you're willing to spend. If you're looking for a cheap entry-level telescope, I would recommend the biggest Dobsonian. That's essentially an undriven alt-azimuth mounted Newtonian reflector that you can afford. It's the cheapest way to get aperture. Light buckets give you a lot of versatility. They're great for looking at faint objects, and they will give you good views of the planets. However, they're not typically driven, and that means that you have to find the objects yourself and track them yourself. My next choice would probably be an alt-azimuth mounted Schmidt go-to scope. Relatively good value for money in terms of aperture per dollar, and the scopes are driven, which allows potential for astrophotography. For casual stargazing use, and if cost really isn't an issue, I would probably go for an alt-azimuth mounted 4-inch apochromatic type refractor. Fast to set up, beautiful to use, and due to the build quality on the instruments, collimation of the optics is essentially never required. Now, the build quality on scopes these days is all around fairly reproducibly high, but of course this is the internet age, and when you're actually thinking of buying a scope, go to somewhere like Amazon and check out the ratings. After that, the cosmos is yours to explore. In the sidebar there is a description of some of the telescopes I bought and used over the years, ranging in price from about $30,000 to $3,000.
Right, this is a normal setup for a telescope where you put your eyepiece in, slid down into this locking collar, and this is the piece you would possibly order off eBay or wherever. I got this one off China, and what this does is it basically comes like this, and you can unscrew. Let me loosen it up. This housing out here where you drop your eyepieces in down inside. If I can come out, your eyepiece, which normally goes in your telescope like that, this, you simply drop your eyepiece in, or so you think, so it fits all the way down in. As you can see there, you tighten this up, and you have, right now I'm running a 25 millimeter eyepiece, and locked it in. So if you got that, and this piece here will slide over that, and you can adjust your focal length and whatnot with that. And you should have your T-ring adapter, which is right here. When you hear of T-ring adapters, this is what they're talking about. And that piece there will fit onto your Nikon digital camera. Now there should be a white dot. You put it on, lock it on. Now you can only run in manual mode this way. So when you get it, you put all this together, screw that piece on, nice and tight. Like I said, I got my 25mm eyepiece in. You'd think you'd simply pull your eyepiece out of your telescope and slide this in just like this. The problem with that is you can't get a far enough focus. You can only focus the close things, and that's where there's questions on another video I put where people was trying to figure it out. But the key to it is taking this end cap off, which is threaded on there, basically setting it to the side, and then unscrewing off your adapter to hold the eyepiece on. This locking, wherever I got this one off China. And what this does is it basically comes like this, and you can unscrew. Let me loosen it up. This housing out here where you drop your eyepieces in, down inside. If I can get it to come out, your eyepiece, which normally goes in your telescope like that, this, you simply drop your eyepiece in, or so you think, so it fits all the way down in. As you can see there, you take a piece, locked it in. So if you got that, and this piece here will slide over that, and you can adjust your focal length and whatnot with that. And you should have your T-ring adapter, which is right here. When you hear of T-ring adapters, this is what they're talking about. And that piece there will fit onto your Nikon digital camera. Now there should be a white dot. You put it on, lock it on. Now you can only run in manual mode this way. So when you get it, you'd put all this together, screw that piece on, nice and tight. Like I said, I got my 25mm eyepiece in. You'd think you'd simply pull your eyepiece out of your telescope and slide this in just like this. The problem with that is you can't get far enough focus. You can only focus the close things, and that's where there's questions on another video I put where people was trying to figure it out. But the key to it is taking this, setting it to the side, and then unscrewing off your adapter to hold the eyepiece on, this locking, and you're going to see there's some threads. Now I'm going to try doing this without taking I better just pull it off the camera. You're going to take this, thread it on. Make sure that's tight. Make sure all your stuff's tight. And then you're going to mount that back in there like that, and this is going to be your setup. You're basically pulling this piece out, this piece here out, which holds your eyepiece in, and you're taking this small piece off your telescope adapter that you had purchased, which that brings everything in closer to the scope itself. Now we're going to go ahead, I'll get the camera turned around, I'm going to turn it on, and we'll see if we can see the moon. Focus it in again, and here you go. There's the moon. That's with a 25 mil. It is doable, and I'm running. a 25 millimeter lens on here. Now we're going behind some clouds. So we're looking at a 9 millimeter lens. See if I can move this a little bit. Now let's try to go down to a 6 or so. 12.5 millimeter lens is what you're looking through right now. That seems to work pretty good for viewing the moon.
Have this kind of ring, Celestron T-ring for the Canon, because I use a Canon camera. If you have Nikon, you would have a T-ring for Nikon. So this thing looks basically like this. Let me see so that I can see. Yeah, it looks like this ring, and it will be written on it for which camera it's suitable for. Now what I will do here is I will take out my eyepiece, and then I will take out the 1.25 inch. Oh, the batteries are short. Okay, then I will unscrew. You have to unscrew this one to separate out the thin barrel. Let's see if we can do this on low battery. Alright, now you have here, this one you will connect with this one here, and then screw them together. Yeah, just screwing them. Okay, now it's ready and can be placed for the telescope. Then your camera, you remove your lens carefully and gently. And then you have to find this white dot here and have it together with this white dot here, and then it's closed like this, and then the camera is ready to be attached to the telescope. Of course you have to be really careful and lock these screws really hard, and then you are ready for your photography, astrophotography. With this setup you can take some nice photos of the moon and of the sun if you have a solar filter, and then if you have a mount with the engines that will follow the stars, you are able to take some photos of deep sky as well. Yeah, so let me now put it back here, and then simply release this one. My hands are in the way, and again what I can do is that I just touch this button here on the camera and I release this ring like this and put back my camera lens. Then I unscrew this one. This one goes off, the T-ring is here, and I screw together the 1.25 inch adapter, and then I'm ready to do the visual observations again. Alright, I hope this helps. So this is what you need to get if you have this Skywatcher 150